Hi guys, welcome. It is week 12 this week. We're looking at lesson 108, 109 for one of our days, and then 110 for the other. So three lessons to get through this week, and then 110 means we're finishing unit 11, so we'll start reviewing that in the following week. So looking at lesson 108, in this lesson we're looking at transformation. So transformation, you probably heard that word, it means a change of some sort. So when it applies to our different polygons or some shapes that we've worked with, there's a lot of different transformations that we can fit. So if we look at ABC and XYZ, they're congruent, ABC and XYZ, meaning they're exactly the same, all the side lengths and angle measurements are the same, but how could we get from this position to this position? Okay, well, we can rotate, which means, again, we can rotate clockwise, counterclockwise, we can rotate, usually we do 90, 180, 270, or getting back to the start would be 360. It's not always that we can rotate 25.7 degrees, but most of the ones we'll see will be quarter turn, half turn, 3/4, or a full turn, which would be right back where we started. So we do this, and then we slide or we translate it. So we rotate and then we translate it to see which sides correspond. So a translation is a slide. A rotation, just like it sounds. So we rotate, we look at a clock and see that the hour hand and minute hand and second hand all rotate. That's what it is. You're just rotating around a pivot point. Translation, think of it like a slide. We're sliding up or down, and we'll see these in the coordinate plane where we're moving right or left or up or down, or a combination like to the right and down or up and to the left. So that's just a slide. So it's not getting bigger or smaller, it's just changing positions. A reflection, here we have A, B, C, and then we have a reflection point which acts as a mirror. Now again, if you've ever looked in a mirror, you get closer to the mirror and it appears that things are getting bigger. If you move away from the mirror, it looks like things are getting smaller. Put one hand close, it's going to look like the other hand is getting close. So these are all transformations. There's some other ones we'll talk about, like a contraction and a dilation, where we're getting bigger, smaller. The ones that looks like that we're working with today, they're all going to be similar. They're not going to change size or shape. We're just going to be rotating, which is turning a figure about a certain point. Translation, sliding a figure in one direction without turning. And then a reflection, reflecting a figure as a mirror, or flipping a figure over a certain line. And we're probably not going to do this just for time's sake. These, if you want to play around with them and do some reflections and different things like that, we'll watch a video on some of the different ones. Whereas you have something like this, which is a reflection, slide, rotation, reflection, and then, as I said, we'll get a lot more comfortable with putting these figures into a coordinate plane, and then down the road we'll see dilations, contractions, where they're getting bigger and smaller, slides, moving left or right, up or down, reflections, where like this one is, the y-axis is acting as the mirror, so to speak. So C is further away here, so C prime is going to be further away here. So we'll go over these together. Just know those different terms, and we'll go over these practice set examples together. Next lesson, similar figures and corresponding parts. Just continue on with what we talked about. So if we're saying that the parts are corresponding, that means that we're looking at which angles or side lengths correspond or are basically matched up. If we were to put this one, rotate it and slide it and do all the things to make this overlap, where would angle C go, where would angle A, and where would angle B? And so angle A would go up with X, C is the right angle, so that would clearly go with Z, and then B would be down here with Y. And then AB would be XY, ZY would be CD, and so on and so forth. And again, we don't always just assume in looking at it. We have an angle indication, which makes it easier. We don't just say, oh, this one looks like this side length. We have to be sure when we're doing it. And the way it reads, that'll help us out. So ABC, A, B, C, X, Y, Z. So X is our starting point. So X is first, A is first. So those have to correspond. B, okay, B is down here. Y is down here. So B and Y have to correspond. And then C and Z have to correspond, which, as we said, they do because those are both the right angles. So the order we read on when we're talking about corresponding and congruent figures does matter. Or maybe just say this is triangle BCA, ACB, BAC, it doesn't matter. And it doesn't, but when we're talking about corresponding, we have to make sure that we're going in the same order, ABC, as their corresponding angles, XYZ. Okay, so that will help you out if you want. I know we've seen some questions like that on the test, or you will see questions like that on the test. Just pay attention to the order they go in. These figures are congruent. What is the perimeter of each? So if we rotated and got them up, so the 4-inch side and the 4-inch side, and then this being across from the right angle, this being across from the right angle, we know this has to be 5 because this is 5. And then this would become this, so that is our 3-inch side. So we know this is a 3, 4, 5 right triangle. Okay, so if we're wanting to find the perimeter, we just add up that. If we want to find the area, we do base times height divided by 2. Now, similar figures, they're the same shape, and all the angle measurements are the same, but they're not going to be the same size. They're not necessarily the same size. Obviously, if they're similar and everything's the same, we would call it congruent. So like 1 and 2, those are congruent. Angle's the same, angle's the same. This angle and this angle and this angle and this angle, and then all of the side lengths are exactly the same. And we'll pull that down here. 1 and 3 look like they're similar, and 2 and 3 also, because 1 and 2 are congruent, so we could say about 1 or 2. 1 and 3 look like they're similar because they have a right angle. It looks like this side and this side are the same length, just like this side and this side, which would mean these angle measurements are the same. It looks like a 45, 45, 90 triangle here and here. Again, we're not just saying, oh, it looks. We have to be given some angle measurements and some side lengths to confirm that. But for these, we're just looking at. So 1 and 2, congruent. 1 and 3, similar. 1 and 4, well, there's no right angle, so none of the angles are the same. So it's not similar, and it's definitely not congruent. So if the two triangles are similar, what is the measure of angle A? And so if we were to put this on its side, and that would make it a reflection of itself, or to stand this one upright and flip it so B was out. Again, you don't have to redraw them in the corresponding sides so that way they're in the same position. It may help, like in this example, once we have it drawn so that this side and this side are corresponding and they're both upright. The base and the base correspond, and then the hypotenuse and the hypotenuse, that'll make it easier to see. Well, A has to be 30 because this angle is 30, and B has to be 60 because this angle is 60. So 2 important things that we already mentioned, but make sure you understand the corresponding angles of similar polygons are congruent. So even though this triangle is obviously bigger than this triangle, the angle measurements were still the same. So it's like in an equilateral triangle, for example. We have an equilateral triangle. Bigger, obviously, these side lengths are not the same. They are going to be proportional. So let's say this is 3 by 3 by 3, and this one is 6 by 6 by 6. So we doubled it. Side lengths are not the same, but they're still proportional. 3 times 2 is 6. 3 times 2 is 6. 3 times 2 is 6. So we can say 6 divided by 3 is 2. 6 divided by 3 is 2. And all of these angles, we know of any equilateral triangle, are always 60 degrees. Same thing here. That's what it's saying, that the angles that correspond or the same measurement. So side lengths are proportional, but the angles are exactly the same. All right, example 3, the two rectangles are similar, so not the same size, which is pretty evident, but make sure, again, don't just assume, oh, they look the same or they don't look the same. Let's make sure we're using some mathematical reason to come up with it. So let me redraw this so we can talk about it. Putting down what we have for that example. All right, the two rectangles, so looking back at example 3, the two rectangles below are similar. What is the ratio of the corresponding sides? What is the scale factor of rectangle ABCD? By what scale factor is ABCD larger than rectangle EFGH? So this one. Well, we know. We look at corresponding sides. Well, 2 divided by 1 is 2 divided by 1, or just 2, so it's 2 times bigger. This one is 2 times bigger than this one. So to go from here to here, we got to multiply from our side lengths by 2. Obviously, the angles are the same. It's a rectangle, so all of these are right angles. So we could draw it in if we wanted to. So to get from 4 to 2, we got to divide by 2 and multiply by 1/2. Get from the smaller one to the larger one, we got to multiply by 2. And again, side lengths proportional. 4 divided by 2 is 2. 2 divided by 1 is 2. So our side lengths are still proportional. Not the same, but they're proportional. So these rectangles are obviously similar, but not congruent. All right, we'll go over these. It's got a lot of just kind of terminology and true-false questions. So we'll look at those when we get into class. The last lesson we're looking at for this week is symmetry. And this one, we'll do some examples on the board and go over. It's going to be difficult to do here, but when we're talking about symmetry, we can divide in a shape. Does it look like it has a mirror image of itself? So we have first what's called a line of symmetry. We zoom in on this triangle and we draw a line through it. Yes, it looks like this and this are mirror images of each other. So thus the triangle is symmetrical, and line R is called our line of symmetry. A rectangle has how many lines of symmetry? Let's do our best to a rectangle. Draw straight lines. If we go through here, yeah, I know it's not perfectly drawn, but if we drew it exactly in the middle and with a ruler, it would be symmetrical. If we drew it, cut it in half right there, it would be. What about from corner to corner? Well, if we look at this portion here, and then this portion, those are cut into two congruent right triangles, but it does not, they're not mirror images of each other. So just because it cuts it into two congruent shapes, that doesn't mean it's symmetrical. It's got to be a line of symmetry. So going back to, we had 1 and then 2 lines of symmetry for that rectangle right there. Which of these triangles, so we can see does not appear to be symmetrical? Well, I think we could draw a line through there and it'd be symmetrical. Probably even this one looks equilateral, so it actually got 3 lines of symmetry. This one, yeah, I think we could draw through what looks like a right angle down here and divide it in half. This one for C looks like this side and this side are different lengths. So if we cut it through there, we'd cut it into 2 shapes, but they would not be congruent and they wouldn't be mirror images. So C is the one that looks like it is not symmetrical, and it's not. We also have another thing known as rotational symmetry. A figure has rotational symmetry if the image of the figure reappears in the same position as it is turned less than 1 full turn. Obviously, you go 360 degrees, it's going to end up back where it started. That doesn't count. Easiest ones to think of is quarter, half, 3/4 turn, or 90-degree turn, 180 or 270 degrees. So if we look at this, which one has rotational symmetry? Oh, sorry, I was trying to do something. Okay, take me all the way back there. I thought there was a way to do this. Hey, there we can do that. Okay, so this is a little strategy that you can use in your book, or if you get a test and it's giving you a symbol or a shape or something, and it asks, does it have rotational symmetry? Where you can physically take it and actually rotate it 90, 180, and 270. So again, it's got to look like it appears in its original position. So let's take a look. So kind of imagine these right here. Okay, doesn't look like any of them are back in their original position. Let's do, so that was 90-degree turn. Now we're 180. A and B look like they're in their original position. C, it's still obviously C and D are the same shape, but they don't look like they're back in their original position because this was the top and now it's the bottom. And this is obviously much longer than this base. And then 270, no, none of them look like they're in their original position. Then 360, we end up back where we started. So based on those rotations, yeah, A and B are the ones that have rotational symmetry. Okay, we'll do that practice set together when we get to class. And this is it for Unit 11, so we'll start reviewing. We'll see you guys soon.